In different fields of science, there are areas where we need to be able to identify organisms or different substances that are unique from one another, and so there needs to be a set of formal rules that one can follow in order to make sure that the way that you are naming something is unique to that individual organism or that individual substance. For instance, in biology, we talk about binomial nomenclature, using the genus and the species of the organism to identify it and distinguish it from others. In chemistry, there are certain ways that we want to name chemical compounds so we can make sure that we are able to distinguish between compounds that may have the same elements in them, just different ratios. We need to be able to distinguish between them easily. Now, some substances, besides having a formal chemical name, also have a more common name that they are known by because they are common everyday household chemicals, or they've been known and used for many, many years. Some of these would include baking soda, commonly used in cooking and cleaning. This is actually sodium bicarbonate. When we say, please pass the salt, we actually mean table salt. And it's good to be specific because a salt, there are literally thousands of different types of salts. Salt is a general classification for a type of compound formed when an acid and a base react. But table salt is the specific compound sodium chloride. Right? Vinegar. If you put vinegar on your French fries, or if you use vinegar combined with baking soda for a science fair project to make a volcano, vinegar is actually a dilute solution of acetic acid. One of the first types that we want to take a look at in terms of naming are binary inorganic compounds, and the term binary suggests that these compounds are made up of only two elements. When we look at the formula for a binary compound, the way that we name it is we name the elements in the order that we encounter them. And the positive oxidation number elements, or the cations, are always listed first in a chemical formula. And so we write the name of this element down and don't make any changes to it at all. The next element, the one that has the negative charge to it, is known as the anion, and so we start with the name of that anion, but then to indicate that these two elements are chemically combined together and that this is a compound and not simply just two elements together, we change the ending of the anion to "ide." So for instance, table salt is sodium and chlorine put together. When we would name that, we would change the ending of chlorine, the anion, to "ide," and hence we get sodium chloride. If we take a look at some examples, the first one we have Ba, which is barium, and then S, which is sulfur. So we would start with barium sulfur, but then we change the ending of sulfur to "ide," making it sulfide, and hence the name barium sulfide. In the next one, we have Ca, which is calcium, and O, which is oxygen. Naming that, following the rules we just outlined, would give us calcium oxide. Now, take a moment and please pause the presentation, try the remaining examples, and then restart the presentation when you are finished. ZnF2 would yield the name zinc fluoride. AlCl3 would produce the name aluminum chloride. And H2O is a very familiar one. You can probably identify it right off the bat as water. However, naming it according to the rules that we just outlined, you could name it hydrogen oxide. And sometimes water is referred to as hydrogen oxide, although not very commonly. Now sometimes our cations are going to have more than one oxidation number, and usually we find this to be true with the transition metals and a few others such as tin and lead. And so when we name a compound that has more than an element that could possibly have more than one oxidation number, we need to indicate which oxidation number it truly has in the name. couple of ways that this is accomplished. One way is known as the stock system, and this is the system that uses Roman numerals in parentheses following the name of the cation to indicate exactly which positive charge form it is taking on in that specific instance. And the nice thing about the Roman numerals is it eliminates any guesswork, eliminates the need to consider where on the periodic table the element is in order to determine the charge. The Roman numeral is the positive charge, and it's only used for the cation, so you never have to worry about mixing it up with the negatively charged anions. The stock system is the most common system used today. Historically, though, there is an older system that uses suffixes on the ends of the element names or their Latin names, and this is sometimes referred to as the us versus ic system. And it's a relative system because the OUS and the IC endings don't represent a specific number, but rather which value is less, which oxidation number is the lesser of the two, which one is the greater of the two. The OUS ending is used for the lower oxidation numbers, while the IC ending is used for the higher oxidation numbers. So for instance, iron has a +2 and a +3 form. If we were going to name them with the stock system, we would simply use iron 2 or iron 3 with the appropriate Roman numeral. If we were using this us versus ic system, it would be ferrous, based off of ferrum, the Latin name for iron. Ferrous would be the +2 form of iron. Ferric would be the +3 form of iron. Now, compounds that contain more than two elements, usually we find this with the polyatomic ions, these are sometimes referred to as ternary compounds, ternary meaning more than two. But the naming is pretty much the same, with an important difference. With the anion, which is typically your polyatomic ion, we don't change the ending to IDE. So AlPO4, when we look at that formula, we notice that there's more than two elements. So one thing we need to identify is where does the cation end and where does the anion begin. And for the majority of the compounds we'll deal with, and the polyatomic ions that we looked at, the only positively charged polyatomic ion that we had was ammonium, NH4. So as you examine a formula in an attempt to name it, if the formula starts with anything other than NH4, then the very first element symbol listed is the cation in its entirety. And so that's where you would split the formula between cation and anion. So in AlPO4, it starts with aluminum, and that's it for the cation. Everything past that makes up the anion. And so that will help you to identify the particles that you need to be naming. So Al would be aluminum. PO4 we recognize as the phosphate polyatomic ion. And again, with polyatomic ions, we don't change the ending to IDE. So the name for AlPO4 would be nothing more than aluminum phosphate. When we look at a formula and it contains an element that we know has more than one oxidation number, it's a multivalent cation, such as in the first one here where we have tin. Start off by naming the formula as we've described. Name the cation, name the anion, and the parentheses here help us also to delineate where's the cation, where's the anion. So we see we have some variation of a tin hydroxide here. Now, the trouble is, tin has more than one oxidation state. And so, depending on if we're talking about tin in its +2 form or tin in its +4 form, those compound names still need to be different from one another. We can't just say tin hydroxide. So what we need to do, we have a couple of different choices here. One way that we were able to achieve these formulas was to use the crisscross method, where we took the charges and crisscrossed them down. We can still use that method to reverse. If we reverse the crisscross, the 4 of the hydroxide would be the charge for the tin, and because tin is listed first, we give it a positive charge. So reversing the crisscross would give us +4 for tin and -1 for the hydroxide, and that method will work, and that's fine. However, just as you needed to do a couple of checks when we used the crisscross method originally, so must you also do a check if you use the crisscross method here. what you need to check and verify is the charge that you give to the anion, and make sure that that is in fact correct. And in this case it is. Hydroxide is a -1 charge, so the 4 that we assigned to tin would indeed be correct. If you run into a situation where the charge that you get for the anion is not correct, then whatever multiplication factor you need to use to correct it, you must also do the same for the cation. But in this case, the hydroxide does check out to be -1. It would take 4 of those -1 charged hydroxides to cancel out the charge of 1 tin, and if that tin had a +4 charge. So the name would be tin-4 hydroxide. In the next one, Cr2S3, it's a binary compound, and so for this one we name the cation, we name the anion, and we change the ending, so we would get chromium sulfide. Take a moment, pause the presentation, complete the remaining examples, and then restart the presentation when you're ready to check them. PbSO4 is an example where you need to be careful with using the reverse crisscross method. First of all, the cation is just the Pb, the lead. The anion is made up of the SO4, the sulfate. And if you are reversing your crisscross, you need to realize that the 4 is off limits. Remember, subscripts in polyatomic ions cannot be changed. They should not be touched. Now, the absence of any parentheses tells us that the subscript on sulfate is actually a 1, because we don't actually write them in. Likewise, we have a subscript for 1 for lead. So if we reverse the crisscross, we would get a +1 for lead and a -1 for sulfate. But if you're using the crisscross method, always double check the anion's charge. And by reversing the crisscross, we've assigned -1 to sulfate, which we know is incorrect. Sulfate is actually a -2. Well, if sulfate's a -2, and we have 1 lead to 1 sulfate ion, then the lead must be in the +2 form. So the correct name for PbSO4 would actually be lead-2 sulfate. MgO would give us the name magnesium oxide. Cu parentheses NO3 parentheses 2 is another compound where we have one of these multivalent cations. Copper comes in a couple of different forms, +1 and +2 most notably. And so when we correctly name this one, we would get copper 2 nitrate. And the last one here, Hg2O2, at first glance one might think, well, we should be able to reduce those subscripts and just get HgO. But for some reason, we haven't in this particular formula. And the only time we know that we aren't allowed to change or reduce subscripts is if a subscript is part of a polyatomic ion. So that's telling us that somewhere in this formula here is a polyatomic ion, although it appears as if it's a binary compound. Well, if you remember, peroxide has the formula O2 with a -2 charge. And so going from that perspective, if the O2 is really peroxide and not just 2 oxygen atoms, then we get a +1 charge for the mercury, and the name would be mercury 1 peroxide.